In this video, we're going to be talking about solving logarithmic equations. Alright, so we'll go ahead and write down the first example, and then I'm going to show you that a flow chart that I'll give you in class that you'll be allowed to use that will kind of help you decide what the process is for each problem. So this is what the flow chart is going to look like. The first question you're going to ask yourself when you're solving an equation is there a log or a natural log, an ln, in the equation? And the start of this video we're saying yes, it is a logarithmic equation. And so the question is the log on one side or both sides? So when you do these problems, the very first thing you're going to do is condense everything down, and your goal is to have a single log on each side. Or perhaps you could make it so there's just a log on one side of the equation. So that's the first goal. And then after that, if there's a log on both sides of the equation, you can just ditch the logs and solve the equation. If there's a log on the other side, just the one side, then we'll do the Tootsie Roll and turn it into an exponential equation that we can then use our calculator to solve. So for this, I'm going to do one example of each of those. So first, I'm using the properties of logs to condense the left side, because right now there are two logarithms on that side and there should only be one. So I'm going to write this as log base 5. It's a subtraction problem, so I know that these two things are being divided. And then I have a log base 5 on the other side. And at this point, once I have a log on both sides like this, I can ditch the logs. So I've got 2x squared over 7 equals 56. And now this is just a pretty simple equation to solve. I just need to multiply this side by 7, multiply that side by 7, and that number is 392. No, I did not know that. I had to look at my notes. Divide each side by 2. X squared is 196. And then after that, I'm going to square root, and we just have to make sure that we are careful to remember that anytime I square root something, I get a plus or a minus version, and that was a perfect square, so the square root of that is 14. Now, when you're solving log equations, it's really important that you double check to make sure that your answer is not an extraneous solution, because oftentimes they are. So the thing that we have to remember is that whatever number you take a log of cannot be 0 and it cannot be negative. So it has to be greater than 0. So when I'm not going to worry about this or this because I'm not plugging in an x value there. But over here, if I did 2 times positive 14 squared, then that would be bigger than 0 and it'd be bigger than a negative. And then if I did 2 times negative 14 squared, that would also work because I'm squaring the negative, which would get rid of it. So in this case, both of those answers are correct. And we can go ahead and use each of them. Okay, for the next example, we're going to go ahead and write log base 6 of x plus 5 plus log base 6 of x plus 4 equals 1. So again, based off the flow chart, we're going to start in the exact same place. This is a logarithmic equation. We're going to start by condensing each side to make sure that there's only one log on each side. So we've got 2 right here, so I'm going to write this as log base 6. And since this is a plus sign, we're multiplying those two things together. So I have x plus 5 is being multiplied by x plus 4. And you can FOIL those now, or you can FOIL them later. It doesn't matter. I'm going to go ahead and FOIL them now. So I would have x squared plus 4x plus 5x makes 9. And then 5 times 4 is 20. And at this point now we have a log on one side. So if we look at the flow chart, it says if you have a log on one side to do the Tootsie Roll or the scorpion or the circle or the cloud, whatever you want to call it, and we're turning it into an exponential equation. So I'm going to start with the base. The base becomes the base. 6 to the 1 power equals all this stuff. And 6 to the 1 is just 6. That's not really anything. So I'm going to make this equal 0 because I'm recognizing this is a quadratic, which means it has to equal 0, and then I'm going to have to factor or use the quadratic equation to solve. It does not matter which one you use. And then when I look at this one, I can see that the numbers that multiply to 14 and add to 9 would be 7 and 2. So in my parentheses, I have x plus 7 and x plus 2. So x equals negative 7, x equals negative 2. And then before I say these are the answers, I have to go back and look at my equation itself. So right here, I know that when I plug my answer in here, this overall has to be greater than 0. When I plug it in here, this has to be greater than 0. So if I plug negative 7 in right here, negative 7 plus 5 is negative 2. That's not allowed. So x equals negative 7. I don't have to check it anywhere else. I automatically know it's extraneous. It does not work. Now if I check negative 2, negative 2 plus 5 is 3, so that one works. Negative 2 plus 4 is 2, and that one works. And so I'm going to say that x equals negative 2 is a valid solution. And as it turns out, the only solution to this problem. All right, next on your notes, we're going to talk about solving exponential equations, which we have actually already done, but these ones are not ones you can change the base on. Exponential. I can't talk and spell things correctly at the same time. So solving exponential equations, but this time we're going to do it with logarithms. So for the first example, we're going to be solving 6 to the 2x plus 1 equals 13. And again, you would be able to look at your flow chart to help you decide what method you're going to use. So in this problem, are there logs or natural logs? The answer to that is no. It's an exponential equation. Can I get the same base? So can I use that chart with the bases to make the base the same? And between 6 and 13, I definitely cannot. So here it says Tootsie Roll or log both sides. There are two ways to solve these problems, and I'm going to show you both of the ways, and then I'm just going to let you do it the way that you prefer to do it. So for this one, the first way is to Tootsie Roll. So my base becomes the base of the log of 13 equals 2x plus 1. And now at this point, I need to get x all by itself. And I'm not going to plug, I could start plugging stuff into my calculator, but I'm not going to do that yet. I'm going to do what is called the exact answer. It's how you write the answer without decimals. And then after I have the exact answer all written out, then I'm going to plug it in the calculator. So divide by 2, divide by 2. So if I wanted the exact answer, that would be the exact answer. You could also have put parentheses around this and just put a 1/2 in front. That would have been fine. And these are usually kind of terrible decimals. So on a new school calculator, or your own calculator, you can hit alpha y equals to get that fraction in there. And then I'm going to hit the math button, log base 6 of 13. The takeaway 1 was not part of me making a log out of the equation, so the -1 should be outside of the parentheses, and then overall I'm dividing it by 2, and so I get x is approximately 0.216. Alright, the alternate method for solving that exact same problem is to put the word log on each side. So I'm going to say log 6 to the 2x plus 1 equals log 13. So I'm allowed to do that because I did it to both of the sides. And then the property of logs tells us to move this to the front. So I've got the exponent has moved to the front. Now, log of 6 is really just a decimal number, so I'm actually able to distribute it inside those parentheses. So I have 2x is being multiplied by log 6, and I have 1 is being multiplied by log 6. And at this point, what I want to do is get everything away from the x. So first, I could minus the log 6 over to the other side. So I have 2x times log 6 equals log 13 minus log 6. and then I want to divide by everything that's not x, because these things are all being multiplied together. So I'm going to divide by the 2 to get rid of that, but I'm also going to divide by the log 6 to get rid of that. So divided by 2 log 6. So the exact form for this would be log 13 minus log 6 over 2 log 6. And again, if I was to type that in, now here we're not using logs with bases, so I can use the actual log button on my calculator. So log 13 minus log 6 divided by 2 log 6. And you'll notice we got the exact same answer. So it really just comes down to what you are most comfortable doing for your solution method on that. Okay, for the next example, we have 14 equals e to the negative 6x. Again, we can Tootsie Roll this problem, so that's what I'm going to do first. The base becomes the base, so I have a log base e of 14 equals negative 6x. And then if you guys remember, log base e is actually ln. So I'm going to write ln 14 equals negative 6x, and then I'm going to divide by negative 6. So the exact answer is that x equals ln 14 over negative 6, and the approximate answer is negative 0.43, well, 440 is what it would be. Because 39 is followed by an 8, so that rounds up to 40. If you were to do the option where you log both sides, in this case you wouldn't log both sides, you would actually ln both sides, because that's what would get rid of the e. So I would write ln 14 equals ln e to the negative 6x. These would cancel because they're opposites of each other. So then I would have ln 14 equals negative 6x, and this one ends up looking identical, so I'm not going to solve it again. So we'll just say from here you can look at those two answers. Okay, and then there's one last thing. So here, we're going to do one equation. These are the most complicated ones. I will not be throwing lots of these at you, but it's important to know how to do them. This is if you have two bases that you cannot change to become the same, and you have exponents on each of those with x's in them. So on this one, you cannot Tootsie Roll this very easily, so I'm not going to show it to you. It's actually very complicated. So on this one, we're just going to log both sides. So I'm going to say log of 3 to the 2x plus 5 equals log of 4 to the negative x plus 4. And then in both of these, we're going to take the exponents and move them to the front. So I've got 2x plus 5 being multiplied by log 3, and I have negative x plus 4 being multiplied by log 4. And then if you guys remember from that previous example, this just represents a number, so I'm going to distribute that number inside the parentheses. I'm going to do that on each side. So I've got 2x log 3 plus 5 log 3. And that's negative x log 4 plus 4 log 4. And then you'll notice that I've got two pieces with logs and x's, and two pieces with logs without x's. And my goal is to get the x's to one side. So what I'm going to do is I'm going to minus this log over so that my logs without x's are on the right side. And then I'm going to add this one so that my logs with x's are on the left side. Now, so that's gone and that's gone. Now, these are not considered like terms because they are logs of different numbers. So I'm just going to write this as 2x log 3 plus x log 4. And then over here I have the 4 log 4 minus 5 log 3. And I know this seems really complicated, but we're actually almost done. So if you notice here, these things are all being multiplied and these are all being multiplied, but between the two we have a GCF of x. There's an x in common in both of these things, so I'm going to take out the x, and then I'm just going to write everything that's left over. So I have a 2 left over and a log 3, and then I have a log 4 left over. And what you'll notice is that now that we have taken out that x, we are, I wrote an S instead of a 3 because I was talking, we are more ready to have that x actually by itself. So at this point, these are all just numbers that are being multiplied by x. So if I want x alone, I just have to divide by that entire thing. So the exact value for x would be this whole nasty fraction. And then for the approximate value, we would actually plug that in. So 4 log 4 minus 5 log 3 divided by 2 log 3 plus log 4. So that is approximately 0.015.